This is practice midterm number 3, problems 47 through 49. And the question is, indicate if the bond order of the following compounds is A, 1, B, 1.5, or 1 in the HIF, C, 2, D, 2 in the HIF, or 2.5, or E, 3. And the compounds we're given are for 47, nitrogen, 48, the nitrogen cation, nitrogen plus, N2 plus, and 49, O2, or oxygen. Now, in order to answer this question, we have to take advantage of the ordering of molecular orbitals. And the fact that when we, for lithium, dilithium through nitrogen, we have the following ordering of the molecular orbitals. And the key feature is whether or not this sigma 2p molecular orbital lies above or below that energy of the pi 2p molecular orbital combination. For lithium through nitrogen, the pi 2p molecular orbital is lower than that of the sigma 2p molecular orbital. Whereas for oxygen through fluorine, the sigma 2p Z actually lies lower than the pi 2p molecular orbital combinations, which are the pi 2px and pi 2py if we want to get technical. That means that this is going to give us a different way of filling up these molecular orbitals, and it's going to give us a population of the electrons that when we go to calculate the bond order, which is going to be 1/2 the number of bonding electrons minus the number of anti-bonding electrons, it's going to, whether we're going to see an increase in the bond order or a decrease in the bond order is going to be contingent on whether we're removing a bonding electron. If a bonding electron is being removed, we're going to see a decrease in the bond order. It's going to be the resulting ion will have a lower bond order. It's going to be a longer bond and a weaker bond. If I remove an anti-bonding electron, I'm going to have an increase in bond order. So the bond order can either increase or decrease when we remove an electron, and it has to do with the highest occupied molecular orbital, the nature of the highest occupied molecular orbital, if it's bonding or anti-bonding. So the features we have to bear in mind are this ordering of the orbitals, and then for answering this question, whether or not we're removing a bonding electron or an anti-bonding electron. And so now let's look at nitrogen. For lithium through nitrogen, I have this ordering of the molecular orbitals. So that's to just go place the electrons in. The electrons, I have 5 electrons from each nitrogen, so that gives me 10 electrons I'm going to place into these orbitals. And I'm going to follow Hund's rule: 2, 3, 4, 5, 6, 7, 8, 9, 10. And so my bond order is equal to 1/2. And it's going to be, I have 2, 4, 6, 8 bonding electrons minus, and I've only got 2 anti-bonding electrons, equals 3. So I have a net triple bond, and that is consistent with what we already know with nitrogen. And so the answer to 47 is going to be E. So you fill in the E bubble on your scantron. Now, this brings us right to the point. 48 is the dinitrogen cation, so I'm removing 1 electron. So I have to look at what is, which electron am I going to remove? It's going to be the most easily removed electron, or the highest occupied molecular orbital, which is a bonding orbital. So I already know I'm going to have a decrease in the bond order. The resulting ion is going to have have a longer bond and a weaker bond than the parent molecule. So if I remove one of these electrons, my bond order is equal to 1/2. Now this time I've got 7 minus 2 equals 5 halves, or 5/5, which is 2.5. So there's a net decrease in bond order, which is what we'd expect. We were removing a bonding electron. And so the answer to 48 is D. That would be 2.5. Now with 49, I have oxygen, O2. Well, this is the order of the molecular orbitals for oxygen through fluorine. Now I'm going to place in the electrons. So I've got oxygen group 6, so there's 6 times 2, 12 electrons I'm going to place in, following Hund's rule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this reveals a lot of the features of oxygen. First of all, I've got a couple of unpaired electrons. It's a paramagnetic molecule. But the main feature is the highest occupied molecular orbital, in this case, is in antibonding orbital. So if I were to remove an electron from oxygen, as it may be happening on the test, because we're going to have this type of question, but I'm not going to say it's going to be nitrogen in this case that's ionized. It could be an oxygen. And if that were so, well, first of all, the bond order to oxygen, the bond order for O2, is equal to 1/2. And I've got 2, 4, 6, 8 bonding electrons minus 2, 4 antibonding electrons equals a net double bond, which is what we expect from our Lewis structure. And that gives me the option, let me see, that would be C is going to be the answer for number 49. But let's carry this one step further. What would happen if I were to remove one of these electrons? I'd be removing a antibonding electron, so I would have 8 minus 3, which would be 5/2, which in this case is greater than 2. So the oxygen cation is going to have a shorter bond distance and a stronger bond than the parent O2 molecule, which is completely different than the behavior which we would predict for nitrogen. And it has to do with the nature of the highest occupied molecular orbital. And, well, although we've just answered this question.